Okay, in this intro video about the photoelectric effect, we're going to talk about just what the setup is for a photoelectric effect experiment, what the phenomena is, and how we would think about it classically. When I say classically, I mean thinking about light as waves, not as photons. So we won't get into the quantum mechanics details until your lab. Right now we're just setting up the idea of what are we talking about. What's the experimental setup? So if you have not already taken the circuit review quiz on Canvas, stop this video and take it now, because I want you to have those ideas in your mind as we move forward. So assuming you have taken that quiz, this is the setup for a photoelectric effect. This is a screen capture from the simulation that you'll be using in your lab. So we have a power supply here where we can change the voltage. We can have various positive voltages or various negative voltages. This battery is connected by wires to a metal plate over here and a metal plate over here. And in between the plates is just a big gap. And in that gap is as close as we can get to vacuum. So not even air or any gas in there, just pure empty space between the two metal plates. This might look a little bit like a capacitor from Physics 2, but this gap is much larger than it would be in a capacitor. So you should not think of this like a capacitor, even though it does have two plates with a gap in between. So right now, in this sketch, the power supply is set to 0 volts, and so it's not surprising that there is no current flowing at the moment. Suppose we do introduce a voltage. So here we've cranked the voltage up to 4 volts, but there is still no current flowing in this scenario. Okay, what this power supply does once we set up a voltage is it sets up a voltage in between the two plates here. We could measure that voltage with a multimeter. Having a voltage means there's an electric field. The electric potential of this plate is higher than the electric potential of this plate. So there's an electric field in the gap, but there is no current. Okay, one of the things that you need to be careful thinking about for the photoelectric effect is this is definitely a scenario that does not obey Ohm's law. We have a voltage in the gap here, but there is no current flowing. So we want to be careful not to try to over-apply Ohm's law. So setting up this voltage does not produce current. Let's think about why that is. So normally in Physics 2, we dealt with complete circuits. In a complete circuit, as long as you give the electrons a little bit of energy, they're able to slide through the metal and circuit will start flowing. But if we have a big gap here, then the electrons need a lot of energy to try to make it from this plate over here all the way over to this plate, to make it across that gap. Right? These electrons are stuck in the metal. It's not exactly the same as how electrons are bound to atoms, the way you talk about them in chemistry, but it's similar. So it takes a lot of energy to rip this electron out of the plate and get it into the gap here. Now remember, if we have a voltage set up, that voltage creates an electric field in the gap. So if we are able to knock this electron out into the gap, then it will be attracted to this positive plate, and it will zoom through this gap and come in over here and contribute to the current. Quick reminder, the force exerted on an electric charge is the charge Q times the electric field. Electrons are negatively charged, which means if the electric field points to the left, an electron feels a force to the right. So if we can knock this electron out, then the voltage will help pull it across to the other side. But this voltage does not knock the electron out of the plate. So how do we get the electron out of the plate? How could we give that electron a lot of energy, so much so that it could jump out of the plate into this gap and then make its way across and contribute to the current? Here we can actually use an idea from Physics 2. In Physics 2, we saw that temperature is related to the average thermal energy of particles in an object. So if we make this plate hot, then the electrons inside the plate will be jiggling around, and as the plate gets hotter, they jiggle more vigorously, and eventually, if the plate is hot enough, an electron can have enough kinetic energy to just break free and get into the gap. So that's what we're illustrating here. We make this plate hot. One way we might do that is just by setting up a second circuit where we run current through a resistor here that gets really hot and heats up this plate. That's what's being shown right here. And if we can knock these electrons out, then even without a voltage, they get knocked out and they'll just keep moseying along. They're already moving. If they get out, they'll keep moving and make it across to the other side where they contribute to current. So this would be a scenario, 0 voltage, but we do have current, all because we have made this plate hot. The hot plate we call the cathode. The other plate that's going to be at room temperature we call the anode. So we're knocking out electrons. Some electrons will be traveling very fast. Other electrons will be traveling more slowly. That's both because at a given temperature, not all the particles have the same amount of kinetic energy. We saw that in physics 2. And it's also because some electrons are bound to the metal more tightly, some are bound more loosely. Not exactly the same as like inner electron shells and outer electron shells in chemistry, but a similar idea. So we make this hot, electrons get knocked out, some are moving fast when they come out, some are moving more slow. And the way we want to think about current is the current we will measure in this circuit is the number of electrons that reach the anode per second. So don't think about the speed of individual electrons. Think about how many electrons get knocked out and make it across to the anode each second. That's what defines current in our photoelectric effect experiment. So let's think about a question similar to what you were asked on the reading quiz, in that case for a simple circuit with just a battery and a resistor. Here's our photoelectric effect circuit. We've got the cathode being made hot so that electrons can get knocked out. Over here our anode is room temperature, so no electrons leave the anode, but electrons, if they're knocked out of the cathode, they could make it across into the anode and contribute current. We want to think about what would the current versus voltage graph look like. Remember, this is a variable power supply, so we can change the voltage in our experiment. Turns out the answer we get looks like this. At 0 volts, we do measure a current from the hot cathode, and as we increase the voltage, that current stays approximately the same. As we make the voltage negative, meaning we make this plate negative and this plate positive, as we make the voltage negative, current gradually decreases until eventually becoming 0. But then instead of going negative, even though we keep making the voltage more and more negative, the current just stays at 0. So very different from the graph you saw in the reading quiz for a battery and a resistor. The next quiz that you'll do on Canvas will walk you through explaining why does this graph look the way it does. So you'll make sense of that soon enough.